Today we have our two last classes. We have one lecture and one seminar on R. According to the study office, our exam is scheduled to the 22nd, I think. Let me check this. Yes. According to the preliminary schedule, your exam will be held on the 22nd of October. This will be Friday. We are going to start at 10 o'clock. Also, today we will have a short test, a quick test for 15 minutes. Okay, let's start. Let me share my screen. Okay, today we're going to study some basics on spatial regressions. We consider different motivations for spatial regressions, how to apply, how to include or incorporate spatial dependence into regressions. Also, we're going to consider several diagnostic tests to choose which spatial regression is best for our model. The outline of this lecture is as follows. First, we consider different specifications for spatial regressions. Then we consider different motivations for spatial models. Then we consider LM tests for spatial regression decision process. And also I will pay your attention for interpretation of spatial regression parameters. Okay, let's start.
Диана? Странно, окей.
I'm sorry, I had an internet problem. Let me start again. Can you hear me?
Yes, again.
Oh, thanks. Let's start from the linear regression model with no spatial dependence, just the dependent variable and a set of explanatory variable with X matrix. In order to include spatial dependence into the regression, we should use spatial weights, Wij, or if we use a matrix notation, we can include spatial matrix. Using spatial matrix, we can construct spatial lags for the dependent variable. Then we get Wy. For the explanatory variables, then we get W multiplied by X, or for the error term, W epsilon. Then we can include these new terms into regressions. Let's consider several different types of spatial regressions. For example, if we include the spatial lag of a dependent variable, Wy, we can include this term with the coefficient, which is rho, to this equation, and we get this new model. This model is called spatial autoregressive model. Autoregressive, that is, our dependent variable depends on its autoregressive term, which is formed by spatial weights. Then we can explain the model like this. The dependent variable for my region depends on values of a dependent variable of neighbors and the explanatory variables of my region. Let's consider the spatial lag of the error term. That is, we include W epsilon, and yes, Y is a vector here. That's right. Y is a vector, X is a matrix, W is matrix, beta is a vector. Okay, for the next equation, we include spatial lag of the error term. That is, we say that in the main regression, the error term is spatially autocorrelated. Then we get the so-called spatial error model. Also, we can construct a spatial lag for the X variables. That is, we include Wx, and we get a spatial lag of X model. We can interpret this model like this, that the dependent variable of my region depends on characteristics of my region and characteristics of neighboring regions. Also, we can include not only a spatial lag of X, but a spatial lag of Y, and we get a spatial Darwin model. To interpret this model, we can say that the dependent variable of my region depends on dependent variable values of neighboring regions. Also, depends on my characteristics, also depends on characteristics of my neighbors. So we can include different, so we can construct different specifications, which is what is rather strange in these regressions is that we get y on the left-hand side and on the right-hand side. Both sides include the dependent variable. So we need to consider such cases in detail. Let's start from the spatial autoregressive model. Also, this can be called a mixed regressive spatial autoregressive model. Consider this equation. Then we
Sorry.
Question.
Sorry. Can you repeat again what is the mean of rho and wy?
Wy is a spatial lag of the dependent variable. We construct spatial weights, that is, let me draw, just a second, let me draw a matrix. Uh, 0, W, 1, 2, W, 1, 3, W, 2, 1, 0, W, 2, 3, W, 3, 1, W, 3, 2, and 0. Consider that we have only 3 regions, 3 observations. And we can construct a spatial weights for them, indicating that the strength or the intensity of interaction between the first and the second regions is W12, сила пространственного взаимодействия регионов описывается весами. Then we multiply this matrix by either values of x variables or the vector of w, the vector of y. Then we get spatially weighted variables. Then we include the spatially weighted variables into regression. Okay, let's start from the spatial autoregressive model. And we need to discover what to do with this term on the right-hand side. We need to move it to the main dependent variable, to the main term. We have done this. And then we group, and this matrix term, where I is the identity matrix, единичная матрица. вынесли матричный множитель единичная матрица минус ρ W, умноженная на зависимую переменную. So we construct this, and then let me erase something from here. Okay, we then multiply both sides of this equation by the inverse matrix to it. Чтобы избавиться от этого матричного множителя, умножаем обе части матричного равенства на обратную к этой матрице. И при умножении на матрицу соблюдаем порядок умножения, то есть с какой стороны умножаем. We have multiplied both sides of this matrix equation by the inverse matrix. The multiplication is from the left-hand side, multiplied this term, we get the dependent variable. Then we multiply this term and this term. After that, we get the equation 5, which is another form of the spatial autoregressive model. And we can see that the coefficient beta is not the only multiplicator for the x variable. We also have this matrix term, and this matrix term includes spatial weights. То есть появляется множитель, состоящий из пространственных весов. And one of the main problems in spatial regressions is based on this matrix. Because when we have many huge number of observations, for example, thousands of observations, and then we construct spatial weights for them, that is, we get a spatial matrix with huge number of dimension. Also, we need to inverse the matrix. So the estimation methods for spatial regressions, including a spatial lag of y, need to take into account inverse matrices of high orders. Here you can see
excuse
all,
me.
yeah.
Could you please turn back?
Yes, just a second.
Mm-hmm.
Yeah.
So finally we have this equation, yeah, and
Yeah.
we assess betas from this equation, yeah.
Yeah.
They will be well, I mean, when we will get the betas, they will be biased by this matrix form I minus PW, or they will be cleaned of it. So it's very important, I guess.
Beta itself doesn't depend on W, except for beta, we need to estimate ρ as well, because ρ is unknown parameter. There is a good question. Is this matrix always invertible? There must be a problem if a spatial weight matrix is not properly designed. for example, if we have some isolated regions, then the spatial matrix is not connected. For these cases, we need to design a new spatial dependence matrix. So we are going to consider simple cases when a spatial matrix is connected, that is no isolated regions, no islands, and we assume that all the regions interact with at least one region, and no isolated blocks of spatial matrix. Okay, let's jump to this scheme. Let me erase my notes.
Where should we begin reading the scheme?
Just a second. I'm trying to enlarge the screen. Sorry. Okay. This is a classification of spatial regression models. As I told you, we can incorporate a spatial lag of the dependent variable, a spatial lag of the explanatory variable, and a spatial lag of the error term. The model, including all these terms, is this one. Assume that we include the spatial lag of the dependent variable, this term, and a parameter to estimate is rho. Also, we have a spatial lag of x variables, and a vector to estimate is theta. Also, we have a spatial lag of the error term, and a spatial parameter to estimate is lambda. Also, we have a term which is familiar to us, x beta. So there are several parameters to estimate rho, which is a scalar, theta, which is a vector, because we consider a multiple regression, that is, we consider multiple x variables, and a scalar lambda. Also, we have beta. So this is a general nesting spatial model. That is a model, that is a spatial model nesting all the combinations for linear spatial models.
Excuse me.
Yeah.
Could you please one more time describe this model using terms of its components? So which component shows us what?
This term, rho wy, is the spatial lag of a dependent variable. This term, wx theta, is a spatial lag of the explanatory variables. And this term is the spatial lag of the error term.
Okay, thank you.
Then we get different cases.
Excuse me, could I ask about this, about genus? So alpha in is what? It's a
constant term.
Oh, we previously assumed that it's in X, yeah?
I just omitted this for simplicity in my slides. Question? I cannot hear. Okay, then we put theta is 0, lambda is 0, rho is 0, and we get different cases. For example, when we put theta is 0, that is no spatial lag of the explanatory variables. Then we get spatial autoregressive combined model. Also, when we consider that lambda is 0, we get the spatial Darwin model. Also, we can get spatial Darwin error model, and so on. So we can construct different spatial regression models. Let's consider different motivations for spatial models. In which cases, which model is the best? Which model explains the story behind the regression? Let's start from...
Excuse me, shouldn't we just try to use a GNS in every case? So it's the most complicated one, and it includes every...
all the combinations.
Yes.
Yeah, it's not necessary. It's not necessary, and this well, if our economic problem does not imply the presence of spatial dependencies, we need not to estimate the general nesting spatial model. Let's consider different stories. A time dependence motivation. Let's consider that our dependent variable at time t is yt. Assume that it depends on neighboring values observed during the previous time period. We can consider the example like these: house prices. House prices for today usually depend on house prices of my neighbors as of, say, yesterday. Imagine that you are going to sell your property. You don't know its price for today, you don't know its price for yesterday, but you can get information about yesterday prices for your neighbors. That is, you can Google some internet sites with property prices, and the prices will be and the prices are available for the past time period. Also, the property price depends on its own characteristics, and usually the characteristics are fixed over time. That is, the number of rooms, the area, and so on. Then we can construct the space-time lagged autoregressive process, that the dependent variable depends on the neighboring dependent variable values for neighbors, and the own characteristics, and we get this equation. For example, this picture is for house prices in St. Petersburg, and we can see that there is spatial dependence between the house prices.
Excuse me. Could you please repeat one more time the logic of our actions shortly?
Sorry. Now we're constructing a spatial regression, and we model the dependent variable according to this scheme, that our dependent variable depends on the characteristics of my observation and the dependent variable of the neighboring observations for the previous time period. Let's modify this equation using this. Replace t by t minus 1. We get, instead of this, instead of t minus 1, instead of t minus 1, t minus 2, and so on. We get this one. Then we substitute yt2, substitute. Then we open the parentheses. Let's substitute over q periods, and we modify the equation. And after the transformation, we get this rather long equation. After that, we can regroup the terms, and we regroup using the main terms w, y variable, x variable, and the error term. After that, we use that the expected value for epsilon is 0. Then we will get that the expected value for u is 0. Also, we can use this term as a geometric progression. Видим, что здесь члены бесконечно убывающей геометрической прогрессии, then we get this, instead of this term, this one. I is a identity matrix, единичная матрица. And instead of this term, we get the inverse matrix. After that, we get the cross-sectional spatial autoregressive model. That is, the cross-sectional spatial autoregressive model arises from time dependence of decisions by economic agents located at various points in space when decisions depend on those of neighbors. So we can explain the story when the house prices depend on characteristics of houses. Also, the house prices depend on house prices of neighbors as of the previous time period.
So our agent, let's call him or her a representative one. So he he is observing his neighbor's actions, and after that, he takes some decisions.
Yeah. He observes his not actions but values of a dependent variable for his neighbors for the previous time period, and has no information on the dependent variable for this time period for neighbors.
Okay.
Okay. This was the time dependence motivation. Let's consider the second motivation when we have a spatial regression model. Consider an omitted variables motivation. Consider this equation, equation 7. The dependent variable is the sum of two terms, x beta plus z theta. Assume that x and z are independent, and assume that we observe x and do not observe z. If we have both x and z, then we can easily compute beta and theta. But life is tough. Z is not observed. That is the omitted variable. Z is not correlated with the observed vector. Then this term acts as a disturbance term. That is the error term. So the omitted variable can be considered as the disturbance term. We get a normal linear model with IID disturbances. Consider a case that Z exhibits zero covariance with the vector X, but follows the spatial autoregressive model. That the omitted variable is spatially autocorrelated. Then we can rewrite this, and we get the spatial regression model after modifying this, that this term corresponds to spatial autoregressive model. I will skip this and to the final equation we get after transformation. We get the spatial lag of the dependent variable and the spatial lag of explanatory variable. And this is the spatial Darwin model. And usually for regional research, spatial Darwin model is almost the main spatial regression model, because we always have omitted variables problem, missing data, missing information on some regional indicators and so on. So spatial Darwin model is the case for the omitted variables motivation. Also, you can find different motivations for spatial regressions. Here you can find some links. I will skip this slide.
Excuse me. Could you please give an example of the regression of the last time which we have discussed? Maybe I didn't catch it. So the first one was about actions of individual based on his neighbor's previous actions and this one? How can we
The
implement it?
second motivation is for the omitted variables motivation. То есть пропущенная переменная. We have no available variable, but we know that the variable must be in this equation, but we do not observe this. We do not observe this. We don't have the values of z. So we, under the assumption that the omitted variable is spatially autocorrelated, we can get the spatial model, which is the spatial Darwin model.
Okay, thank you.
There's a question in the chat. What if we're concerned with understanding the impact of X, not some omitted variables, not correlated with X? Is it really necessary to use if we do not consider any spatial dependence in the regression, we do not construct a spatial model. For this motivation, we assume that the omitted variable is spatially autocorrelated. Because for regional research, we usually face a situation when we know that we need an indicator, but we cannot measure it. That is, for us, the variable is unavailable, that is omitted in the regression. And also we know that the values of this variable should be spatially interdependent, that is spatial autocorrelated. This case leads us to the spatial Darwin model. Okay, there are different stories behind spatial regression models. I will skip this, and I'm going to give another way to choose a spatial model. The first way to choose a spatial model is to motivate it. То есть первая история, как выбрать пространственную регрессионную модель, это объяснить, что за история, что за сказка за вашей экономической проблемой. Второй подход для выбора пространственной регрессии формальный, с помощью теста. The second way to choose the right spatial regression is based on diagnostic tests. First, we start from the non-spatial linear regression model. That is a standard multiple regression. We can estimate this using OLS method. Then we consider residuals of OLS. A week ago, we tested OLS residuals, whether they were spatially autocorrelated. We use Moran's test for this. For that, Moran's test cannot say which model is the best. Is the spatial lag model or spatial error model or spatial Darwin model the best for us? we cannot say it using Moran's test. The Moran's test reveals only spatial autocorrelation in residual values. Anselin proposed the spatial regression decision process based on Lagrange multiplier diagnostic tests or LM tests. We run LM tests. There must be LM error and LM lag. That is, they are related to the spatial error and spatial lag terms in regressions. If both tests are not significant, then we should stop with our OLS regression. If only one is significant, then we should distinguish which one is significant. If LM error test is significant, then we run spatial error model. If only LM lag test is significant, then we run a spatial lag model. If they both are significant, then we run the robust versions of tests. And we consider robust LM error and robust LM lag. If the first one is significant, then we choose spatial error model. If the second one is significant, then spatial lag model. If they are both significant, then we have to look at the p-value. So this is a formal way to choose a spatial regression model. This is a link to the article on this simple diagnostic tests for spatial dependence, which is published in Regional Science and Urban Economics. That this is a general scheme for the LM tests. I will skip this part because we don't have enough time to cover this. I will just show you the practical issue for us, how to use this in our Lagrange multiplier diagnostic tests. We need to use this function lm linear model dot lm tests, Lagrange multiplier tests, and there are parameters of this function. We need to indicate the model using the equation for this. Also, we need spatial weights. Also, we can indicate zero policy. Zero policy means that if there are no weights for some observations, we can just omit them. So usually zero policy is true. Also, we can indicate what kind of test we need to compute. Usually we can run all the tests and then just choose the best one. And the rule is that for the robust tests, we need to use them only when both LM error and LM lag reject the null hypothesis, that is, they are both significant. And we do not use the robust tests when neither error or lag LM tests are significant. And we select a model with most significant statistics. And here you can find a link to more details on this. And let's consider briefly how to interpret parameter estimates. Consider a spatial model. If there is no spatial parameter, so if we consider only the first term, you know how to interpret the beta, the vector beta or its elements. But when we have this term, the spatial lag of the dependent variable, we cannot interpret as usual that we increase the x value and the dependent variable will increase or decrease by value beta. Because we cannot say that we change x and the dependent variable will change on this value. Why? Because we have this term. Для интерпретации пространственных регрессионных моделей стандартный подход, когда мы говорим, что вот при увеличении x на столько-то единиц, на одну единицу y у нас увеличится или уменьшится на бета. Здесь это не сработает по той причине, что у нас есть пространственный лаг y. Потому что мы увеличиваем x, y тоже меняется, но y у нас еще здесь есть. Соседские значения. То есть изменения на y будут не в размере бета, а в каком-то другом размере, поскольку здесь еще вот этот пространственный лаг есть. Поэтому для интерпретации используются специальные расчеты. Я не буду с вас, разумеется, требовать детальных разбирательств, как рассчитываются и как выводятся эти коэффициенты для интерпретации, поскольку это выходит за рамки нашего курса. Но я хочу показать, что коэффициенты при иксах, когда мы все перенесем, все, что связано с y, перенесем в левую часть, все, что с иксами останется в правой части, так вот, эти коэффициенты, они будут не равны бета. Let's modify this equation, equation 17. We need to put all the dependent variables to the left-hand side and all the x variables to the right-hand side. We need to move this part to the left-hand side. Then we get, as we have seen today, let me annotate this. Y minus rho wy is equal to x beta plus theta wx plus epsilon. That is, we have moved this term to this side. And then we need to find the matrix corresponding to W, corresponding to the dependent variable. This is an identity matrix, единичная матрица минус row W матрица, выносим за скобки, and the same terms. Then we need to multiply both parts of the equation by the inverse matrix. That is I minus row W inverse matrix multiplied by x beta plus I minus row W minus 1 theta Wx plus I minus row W minus 1 epsilon. So we can see that the coefficient corresponding to x variables is not equal to beta, because row W is not zero. Если бы здесь вместо вот этой матрицы была бы просто единичная матрица, то да, изменение x на одну единицу скажется на y как увеличение или уменьшение на бета. Но здесь у нас не нулевая матрица, поэтому нужно для интерпретации это учитывать.
Excuse me. And even if we have a zero matrix on the left of x beta, we have some matrices to the left of other x. So they need to be 0 too. All right?
Which
So,
matrix?
yes, here.
Here?
Yes, and one scalar and W after that. Yes.
W x plus epsilon.
Окей, sorry, in Russian. То есть того факта, что матрица, которая стоит слева от xb, была бы единичной, не было бы достаточно, чтобы x увеличился, ну, только на бету при увеличении x на единицу, потому что там еще перед x есть другие коэффициенты во втором слагаемом.
Если бы вот это было бы единичной матрицей, то пространственной взаимосвязи нет. В каком случае это будет единичной матрицей? Ну, когда row W 0. А когда row W 0? Когда все веса нулевые, то есть никто ни с кем пространственно не взаимодействует. Поэтому, как только у нас кто-то с кем-то из объектов, из регионов или там из observations с кем-то пространственно взаимодействует, сразу появляется не нулевая весовая матрица. So, we have this term corresponding to the x variable. So we cannot interpret the impact of the explanatory variable as beta, because beta is not the only multiplier for x. In order to compute the value corresponding to each x, we need to expand this and rewrite the elements for the first observation of a dependent variable, for the second, and so on. And after that, we can get sums of elements, something like this, and we call this as the data generating process. That is the equation forming the dependent variable. Let me jump to the next slide. I will erase this. And in spatial regression models, to interpret parameter estimates of regressions with spatial lag of a dependent variable, the most common interpretation is as follows. The impact of changes in the explanatory variable is split into two effects, direct effect and indirect effect. The direct impact is as follows. The impact of changes in the impact of changes in the explanatory variable for the my observation of a dependent variable implies changes in the dependent variable as a feedback effect crossing through my neighbors. То есть прямой эффект изменения переменной x может быть интерпретирован так. Переменная x увеличивается на 1 единицу, и этот эффект идет через соседей и возвращается на мою зависимую переменную. Находят среднее по всем наблюдениям и называют это average direct effect. Есть еще непрямой эффект. Непрямой эффект, он следующий. Изменение x моего региона отражается на зависимой переменной не моего региона, а моих соседей. То есть два вида эффекта, прямой и непрямой. Прямой эффект, когда изменение объясняющей переменной влияет на зависимую переменную того же региона, этот эффект он идет через соседей и возвращается обратно. А непрямой эффект, когда изменение моих иксов влияет на зависимую переменную моих соседей. Суммарный эффект – это сумма прямого и непрямого эффекта. We are going to consider these effects in more detail during our class. Just a second. Okay. Now we are going to have a short test concluding a previous material on vector data, on spatial weights, and autocorrelation, spatial autocorrelation. Please open LMS. There must be a quick test for you. Can you see this? Is this available?
No.
Just a second, let me check this.
Yes, there is nothing but the slides and some sources.
Projects.
No.
No project, unfortunately.
Okay. Is it available now?
No, still we don't see it.
Перезагрузи.
F5, F5.
У нас там только 11 минут осталось.
А,
Можно расширить немного время?
да, конечно же.
Извините, я правильно понимаю, что R не нужен, да?
Спасибо.
Спасибо.
This is a quick test. You should download this and open this in Microsoft Word and add your answers to the file, then save it, and please upload this.
Извините, а можно просто в чат вам отправить личное сообщение, ответ на тест?
Так, в чате может потеряться, лучше электронное письмо.
Электронное письмо, хорошо.